video, we'll briefly discuss modeling with the Heaviside function. So the Heaviside function, we want to understand how we could actually use this thing, and oftentimes the Heaviside is not used as a standalone. This is the standalone function, and this is recall a 0 or 1 signal. A 0 signal of the Heaviside will be produced up until time A, and after time A, including time A, the signal jumps to a 1. So in and of itself, that may not seem very useful because of the fact that zeros and ones aren't just used by themselves. So this guy right here would equal, not the Laplace, but the Heaviside itself would be 0 for time less than A, and would be 1 for time greater than or equal to A. So that basically tells us that from up until some point time A, the value of the signal is 0. And so we put an open dot at time A because at time A, the signal jumps to a 1. Okay, so this is an important function because it can act as a switching function. It can turn things on or off. Zeros and ones will do that. When you multiply by 0, you get 0, and when you multiply by 1, you get whatever you multiplied it by. So we oftentimes want to multiply it by a function. So in this Laplace transform, we're going to take a Heaviside times some function. But that function isn't just the function itself. It's that function shifted over to the right a units. So for instance, let's say I want to model with maybe some function that looks like this. Maybe what this is right here is this function is t squared plus 9, we'll say. Okay, so that's f of t right there. Okay, but what I really want to do is I want this function to turn on f of t at, we'll just say for argument's sake, t equals 2. Okay, well, if I actually turn this thing on at time equals 2 without shifting it over, then this function will take on that value right there and will have its trajectory from that point on out. But my desire was to actually have this function, which actually starts here at time equals 0, for that point right there to be this point right here. So in other words, what I want to do is I want to take this segment and I want to shift this entire thing over so that it starts here and then projects upwards instead of starting back here. So this point in red right here corresponds to this point in red over here. So what I've effectively done is I've shifted over f of t, shift f of t right 2 units. Now you absolutely don't have to do that, but if my goal was to have this function begin at time 2, then in order for me to preserve the same output it would have at time 0, I've got to shift all the points over to the right. Well, how do you shift a function over? Well, to shift a function over from our college algebra or pre-calculus class, we know that when I shift it over, I've got to evaluate the function at f of t minus 2. So this works because when I plug in a t equals 2 here, what I'm really evaluating is f of 0, and f of 0 is the same as f of 0 back here. So what would this look like? Well, this literally says that replace the input value with t minus 2, and so my shifted function will be t minus 2 squared plus 9. And so this function right here is f of t minus 2. So that's the purpose of this particular Laplace transform, where I want a function to begin, and so that I don't have to hassle with how to do that, I'm basically just going to take the function symbolically and shift it over a units. Now it turns out that mathematically this works out nicely, that if we go through the process of using Laplace transforms, we are going to come up with this little package here, which says that the Laplace transform of a Heaviside times a function shifted to the right, the same number of units at which the Heaviside turns from 0 to 1, then that will result in e to the negative as, where a is the value of the Heaviside, multiplied by the Laplace of f of t. Okay, so this Laplace transform tells me that what I need to do over here is, in order to find the Laplace, I've got to take the function that I have in its unshifted form and find its Laplace. So the Laplace transform of u sub 2 of t times t minus 2 squared plus 9, all that quantity right there, is going to equal, well, e to the negative 2s times the Laplace of the function that I'm working with in its unshifted state. Well, f of t, recall, was our t squared plus 9. So now I just need to find the Laplace transform of t squared plus 9. And revisiting some of our Laplace transform sheets, the Laplace of t squared is going to be 2 factorial, n factorial over s to the n plus 1, where n is the exponent, so this will be s to the third, plus the Laplace transform of 9, and the Laplace transform of 9 is 9 over s, and that's e to the negative 2s multiplied by all of that. So that's how I would work with it in sort of a example sense. Well, let's see how we might actually model with this. So let's suppose that I have a population that experiences 10% exponential growth until time equals 3, at which time periodic harvesting occurs at a rate of h of t equals this amount here. So, and then I have my initial population size is 12. So what I essentially want to do is if I just look at this guy here, my harvesting function, my h of t, then the function 2 sine of 4t plus 1 has a center line of 1, amplitude of 2, and then my frequency here, I'm not going to actually deal with that here, but it's going to look something like this, right? So bad sketch, but what I want to do is I want to take this point right here, and I want to shift that over 3 units so that the sine function begins where it would normally begin at time equals 0 at time equals 3. So I'm going to shift this guy over. I'm going to take h of t minus 3 so that this function does the same thing but at time 3. So it will look like this or something like this. So this guy is h of t shifted to the right 3 units. Okay, well, let's actually build this model. So y is going to be our population size. dt, so we're not actually told what t represents in this problem. I mean, in terms of hours, days, years, etc. Let's suppose it's hours for simplicity. And then we have exponential growth. So that means 10% of the current population size. That's how many more units of population per year we'll get, minus my harvesting function, okay? But I don't want that harvesting function to begin until time 3, so I'm going to take the Heaviside function at time 3 and multiply it by h of t minus 3. Okay, so that means that if I actually figure out what h of t minus 3 is, well, h of t is 2 sine of 4t plus 1. h of t minus 3 will say, take t, replace it with t minus 3. So this will be 2 sine 4 times t minus 3 plus 1. Now, I encourage you to go ahead and graph this in Desmos or some computer package so you can see that if I graph this function right here, it will be the same as 2 sine 4t plus 1 shifted over to the right 2 units. Of course, you will see more of the graph here, but this point right here will correspond to this point over here at time 0. So that means that if I actually expand this out, I'll have u sub 3 of t, this is minus the harvesting, u sub 3 times the harvesting term. So u sub 3 times the first term minus u sub 3 of t times 1. I guess this should have been down in the negative, but that's okay. All right, well, so now we need to actually take the Laplace transform of both sides. So to do that, I'm going to take the Laplace of dy dt, which is s times the Laplace of y, minus the initial condition. And that equals, and I'm going to jump over here because this is what it's actually the equality that I'm going to be working with. So times the Laplace of 0.03y, which is 0.03 times the Laplace of y, factoring out the 0.03, minus the Laplace of this deal here, minus the Laplace of this deal here. Now, this is just minus the Heaviside, and the Heaviside, we know that it is e to the negative as over s. So e to the negative 3 s over s. And that's going back here to our slide, e to the negative as over s. And so that's the third term. Now I'm going to work on the second term. So I need to know what goes here. and that's going to represent the Laplace transform of this function that I have here. Okay, so I'm going to just do that down here. I'm going to say the Laplace of u sub 3 of t times 2 sine of 4 times quantity t minus 3, the Laplace of that whole thing. Okay, well that's going to equal e to the negative as, which is e to the negative 3s, times the Laplace of the function unshifted. In this case, that is, we're calling that h of t. Okay, well this right here, this piece, this is h of t minus 3, and we know that if I take h of t, I'm going to take all the t minus 3's and replace them with t, so h of t will be 2 sine of 4t, and we already know that because that was the function we started with, and then we derived h of t minus 3 from there. All right, well, the Laplace transform of h of t is going to be the Laplace transform of 2 sine of 4t, which, well, 2 is a constant, so I can technically factor that out, times the Laplace of sine 4t is going to be 1 over s squared plus a squared, where a is the coefficient here, so this will be s squared plus 4 squared. And now I have, when I put the pieces together, I have s Laplace of y minus y of 0, which we said was 12. So minus 12 equals 0.03 Laplace of y minus e to the negative 3s. I'll do 2 e to the negative 3s times 1 over s squared plus 4 squared. And I could write 4 squared as 16, but when I inverse Laplace everything, I'll need to write it back in the square form to see what a I'm using, and then minus e to the negative 3s over s. Okay, so I can do a little bit of work here. Now if I do a little bit of algebra, I get my Laplace of y on one side, factor out an s minus 0.03, that'll come from this term here, and that will be equal to negative 2 e to the negative 3s times 1 over s squared plus 4 squared, that term, minus e to the negative 3s over s, which is that term, and then I'll move the 12 over, so I'll have plus 12. And then, of course, we want to isolate Laplace of y, so divide both sides by s minus 0.03, so we'll get an s minus 0.03 in the denominator of this term here, and then we'll get an s minus 0.03 in the denominator of this term here, and then we'll get 12 over s minus 0.03. Now, the algebra gets a little bit cumbersome here, but we could certainly proceed to do Laplace inverse of both sides, and I'll leave that up to you to determine, but in order to actually invert this term here, we would need to do the partial fraction decomposition of this guy, and we would also need to do the partial fraction decomposition of 1 over s times s minus 0.03, and then we already know the inverse of this, that's going to be 12e to the 0.03t power, and then we can find our solution that way. But the goal really of this video was to kind of set up a model and see how we might be able to use that. So feel free to solve it, but that is a way that we can incorporate this periodic harvesting. Now I'm realizing now that I actually used a 3% growth rate instead of the 10% originally posed in the problem. So because we already have it here, we'll change the problem. We'll make it that there was 3% exponential growth rate. So after all is said and done, we now want to analyze our model, and we'll get a function with Heavisides in it, but then if we write it in terms of its pieces, so what we're seeing here is that up until time 3, there is strictly exponential growth, which makes sense. We have a starting population of 12, and we have a 3% growth rate. So we do kind of, I mean, it looks fairly linear because it's a slow growing function. Start off the bat, and then at time 3, we have the Heaviside kick in, which starts to control that oscillatory behavior. And so we start to see right away that we get some oscillations in the population. Now, this is interesting, the fact that we can see pretty clearly that the dominant term here is the exponential term. So because that is part of the solution function, we will still see some of the sinusoidal behavior, albeit less and less, as the exponential piece really starts to project this thing upwards. But we do have these little oscillations since the sine function had a center line of 1 and it had an amplitude of 2. In some cases, the harvesting will be positive. In some cases, it will be negative. So what we can